Hello everybody, Adam Lusek here, and today I wanted to talk about knowledge graph RAG. By now, most of us are familiar with traditional retrieval augmented generation systems, as it's really become a core component in a majority of language model system design. Most of the time, it follows a process that looks a little bit like this: taking your document, you chunk it into workable pieces of text. That is all embedded into a vector database using an embedding model. And then at runtime, what happens is someone inputs a query. That query is also embedded. A semantic similarity calculation is ran across your vector database to retrieve semantically the top n relevant chunks. And then those are, of course, passed through as context to the language model, along with the original query as context to answer the final question. This basic approach is very effective for most initial implementations of RAG-based systems, but comes with a few different downsides as you try and scale up your knowledge base. So as you introduce more complexities into your knowledge base, whether that be additional topics or just more text on the same topic, we start to get bottlenecked by this retrieval step. Simply retrieving just the n number of relevant chunks based on the user's query can miss connections between similarities across your data or broader themes that your information may convey. And so to combat a lot of these limitations, companies like Neo4j and Microsoft have started to create knowledge bases in the form of knowledge graphs instead. So that's what we'll be going over today. A little bit of what knowledge graphs are, how they connect to retrieval augmented generation and are starting to be used, as well as setting up your own knowledge graph and comparing the different techniques and searching capabilities to just a traditional RAG system. So to start, what really is a knowledge graph? I've put this fun example here, but the technical definition is that a knowledge graph is a knowledge base that uses a graph structured data model or topology to represent and operate on data. Knowledge graphs are often used to store interlinked descriptions of entities, which are objects, events, situations, or concepts, while also encoding the free-form semantics or relationships underlying these entities. In our example here up above, we can see some entities here, such as the Mona Lisa, or James and Lily, as well as those semantic relationships between them. So Lily is a friend of James. James likes the Mona Lisa. The Mona Lisa is in the Louvre. Essentially, we're trying to mirror a little bit of human cognition within our data structure by explicitly mapping relationships between objects, concepts, and ideas through both their semantic and relational connections. This very much so parallels how our brains actually understand and internalize information. Not so much as isolated facts, but more as interconnected concepts, how we interact with them, and the different relationships between all of them. As a secondary example, I have this one of coffee with its relationships to brewing, beans, and effects. And so really when we look at something or understand something like coffee, we don't just know that it's a beverage, but we might automatically connect it to different related concepts, like these beans and brewing methods, morning routines, social interactions, whatever you might have over a cup of coffee. And so knowledge graphs aim to capture these natural associations in a structured way. Relating this back to retrieval augmented generation, what we mentioned before is that simple semantic similarity-based retrieval struggles to capture broader conceptual relationships across text chunks. So, knowledge graphs and knowledge graph RAG approaches address this limitation by introducing a structured, hierarchical approach to the actual information organization and the retrieval that we run on our knowledge base. We can take advantage of this structured way of knowing how concepts, ideas, and different entities, which we'll break down in a second here, are actually connected by allowing our system to both start at and traverse these different paths along this graph to be able to more effectively retrieve the right kind of information. One thing to note is that knowledge graphs are not necessarily a new concept per se. They were actually introduced by Google and power a lot of the advanced Google search that we have today. But the issue with knowledge graphs is that traditionally their creation and making a knowledge graph has been a very resource-intensive process. You either had to literally manually build and curate these things, or convert some sort of traditional relational database into a graph-based structure. But now with the advent of large language models, we're actually able to start taking advantage of them for the automated creation of graph-based representations of data. So now what we can do is use their advanced reasoning capabilities across unstructured text, so things like Word documents, PDFs, blog posts, etc., to identify entities, infer relationships, and actually automatically structure the information in a way that was previously a very intensive manual process. So not only can we use knowledge graphs to both create more robust retrieval augmented generation flows, but we can also use language models to actually both create, update, and maintain these knowledge graphs. To show this entire process in action, we'll actually be taking advantage of the aforementioned GraphRAG coming out of Microsoft. This is an open source, graph-based, both knowledge graph creation and retrieval augmented generation tool. There are a lot of advanced concepts within GraphRAG that we're not going to go super duper deep into, but they've implemented a lot of really interesting things to consider that we'll explore at a bit of a higher level to both get an understanding of how knowledge graphs can be created with language models, as well as different advanced querying techniques. So before we break down the technical bits here, I want to reemphasize and highlight the three main components of knowledge graphs. This includes entities, relationships, and communities. An entity in this case is going to be a distinct object, person, place, event, or concept that has been extracted from a chunk of text through a language model analysis. And so entities here are going to form the nodes of our knowledge graph. Relationships then are going to be the different connections between two of our entities or the nodes on our graph. These are also going to be extracted directly from language model analysis over text chunks. And the third main point here are communities. So communities are more so going to be clusters of related entities and the relationships identified through some form of hierarchical community detection. Generally, this is going to be using something like the lead-in algorithm. We're not going to go too much into how that algorithm works for this, but what we can understand about communities is that they create the structured way of understanding different levels of granularity within our knowledge graph, from very broad overviews of concepts at a top level to very detailed local clusters at lower levels. This will really help us in organizing and also navigating these knowledge graphs when we want to retrieve relevant information. So with a little bit of that background out of the way, let's actually get GraphRAG up and running and go over the actual data flow. But first, we need to install GraphRAG. So I've got an empty folder here, and I've passed over to it in my terminal, as well as created a new environment. So the next thing we need to do is make a quick folder for our inputs. So now we're going to have a base folder and then an inputs folder. In the inputs folder is where we're going to put in our documents or our text files that we actually want to create the knowledge graph from. More specifically, I wanted to put in this, the ultimate guide to fine-tuning LLMs from basic to breakthroughs, from the Cedar Ireland Center for AI. I think that this would be a really good example for a knowledge graph since it includes a lot of very similar information. So something like traditional semantic retrieval might struggle to pull very specific information from it, but there are clearly some overarching topics and concepts and relationships between all of these concepts. But more importantly than that, we actually also need to install the GraphRAG package. So Microsoft has made this very easy by just implementing a no-code, low-code GraphRAG package. And now with that installed, I've input our text file of the paper, the fine-tuning guide, into the inputs file. I just converted this very simply from PDF to text and then cleared off the glossary and the abstract and the title page, as well as all the way down at the bottom, the references. So I just want to focus on the main content here. To initialize our environment then, all we need to do is type in GraphRAG init and then an argument for our root, which the root folder here is going to be our rag test folder. So once we do that, we will see a whole lot of files start to pop in. There we go. So now we have all sorts of these prompts, as well as a settings YAML file. The big thing you'll want to do here is open up that YAML file and then insert in your OpenAI API key. So it says GraphRAG API key. You can save it as that, but in my environment variables, I have my OpenAI API key set up here. So I'll just replace that line with this. That'll grab it there. And then also, if you're a little bit cost conscious, you can change the model here to GPT 4o. Similarly, down here for embedding models, we are going to also insert in our OpenAI API key. And after that, that's really all you have to do. One quick clarification is that actually the inputs file should be just input file. But once we have this, we can go ahead and type in GraphRAG index and then say our root file, which is going to be rag test here. And then when we run that, it should just do its thing. And then after a few minutes, it's actually all finished and everything's been created successfully. So now we have a graph and also a queryable RAG graph. But doing this and setting this up doesn't really tell us much about what's going on behind the scenes or how this is actually being created. So let's switch gears and cover a lot of that information, because Microsoft has implemented a lot of really creative ways of approaching both the indexing as well as some of the retrieval steps that we'll get into later. The general data flow when we insert a text file or unstructured data into GraphRAG is going to be that it's loading and splitting the text first into chunks. It is then going to extract entities and relationships with a language model for each chunk. It is then going to merge and summarize the per chunk subgraphs that it creates with those extracted entities and relationships. We will then create embeddings for the nodes specifically, which are going to be those entities, as well as do some form of community detection. Then finally, and this is the interesting step, we're also going to create community reports, which are going to be summarizations of the information actually within communities that are going to be embedded as well. So following along our fine-tuning guide here that was in text form, essentially what happens is that it is first split by default into chunks of 1200 tokens with 100 token overlaps. So I've simulated this very quickly with the token text splitter from LangChain. And then when running this, we can see that we have about 53 chunks. And just looking at one in the middle, we can see what it contains. The next step then is going to be processing these text chunks with a language model to extract the entities and relationships. So to do this, GraphRAG actually uses quite a lengthy prompt here where it shows some examples of how to actually put in the entities as well as the relationships given some chunk of text. But the goal here is going to be given a text document that is relevant to the activity, as well as a generated list of entity types. What it's going to do is identify all of the entities from those given types from this text chunk, and then all of the relationships among the identified entities. So it'll go through first and write down all the entity names, the entity types, and the entity descriptions formatted into this format so that it makes it easy to parse. And then from the entities identified in the first step, what it's going to do is identify pairs of source and target entities that are clearly related to each other. So it'll say the source entity, the target entity, and then the relationship description between them. And then what we also try and do is have some sort of integer score ranked 1 to 10, indicating the strength of the relationship. This will come into play later when we actually merge all of these subgraphs that are created, as all 50 plus of these chunks are ran through this prompt. So once formatting this into a LangChain chain, so we'll have the prompt passing to the language model with a string output parser. If we just pass in the chunk of text, the just shown text chunk 25, and get a response from the model, we'll see that it has returned back this text chunk. So it has a whole bunch of entities here that it is formatting with record delimiters between them, as well as relationships. For this given example down here, looking at an entity of evaluation metrics, it states that evaluation metrics are criteria used to assess the performance of AI models, including metrics like cross entropy, perplexity, factuality, and context relevance. And then a relationship example down here might be evaluation metrics to context relevance. And so it says that context relevance is an evaluation metric that ensures the model uses the most pertinent information for generating responses, and then gives it a strength of 8 out of 10. So this step is ran across all of our text chunks, and then looking at these, all of these per chunk subgraphs, which we've essentially created a small graph for each chunk, are going to be merged together. So any entities with the same name and type are going to be merged by creating a simple array of their descriptions, and then any relationships with the same source and target are merged also by creating an array of their descriptions. The final step is then summarizing these arrays or lists one more time into a single final explanation, given all of the context of the entities and relationships across all of the chunks. So taking a look at my graph, the original one that I created, we can see some of the final entities that we have here. So we have things like GPT-3, GPT-4, BERT, and then also the final description, a little summary of the final description here. Similarly, looking at the relationships here, we can see that GPT-3 is related to GPT-4, says that GPT-4 is an advanced version of GPT-3. GPT-3 is related to ChatGPT. ChatGPT is based on the GPT architecture, etc., etc., so and so. So we now have our final entities and our final relationships between these entities. So essentially we have a full graph, but we can take this one step further. So after we do have the basic graph and entities and relationships among them, what we can do is apply the aforementioned lead-in algorithm to create and group these nodes into different hierarchical related entities or communities. As I briefly discussed, what it's going to try and do is put similar nodes together into these communities at different levels of granularity. So in this simple diagram that we see here, for a level 1 community detection, what we might see is all of our nodes that are nicely connected will algorithmically move the similar nodes closer together. And then what we can do is define these level 1 communities. And then once we kind of aggregate all of these into larger groupings of nodes, we can then again follow the same thing and create a higher up community. So this will be a level 2 community. So you can see as we get closer and closer to the bottom of this, we can have more levels of specificity or broader groupings. Additionally, what we'll be doing is actually also embedding the nodes using the node to vec algorithm. So later on, we'll be able to use the communities as well as the embeddings to allow us to look at both the subtle patterns through embeddings and the obvious connections through communities. Combining all of these relationships, when we take a look, we can see the nodes that we have. So this is starting to get into a much more specific format for these graph-based indexes and setups, but we now finally have all of our nodes nicely organized into different communities as well as levels. But we can actually go one step further with these communities. What GraphRAG implements is community report generation and summarization. So with the clear community groupings, what we can do is actually aggregate all of the main concepts across the different levels and across the different communities into summaries. This will allow us to increasingly capture the groupings of the ideas and get to higher level and higher level ideas as those communities become more broad. Creating these and having these on hand, as well as embedding them into a vector store themselves, is going to be really crucial for some of the actual advanced, broader retrieval techniques that we'll talk about in a second. But what we can see is that loading up our community reports. For community 61, which is at level 2, is going to have a title of Amazon Bedrock and AI model providers. And then if we look at the summary, we can see that this community is centered around Amazon Bedrock, a service by AWS that facilitates access to foundation models. And key entities include AI 21 Labs, Anthropic, Cohere, Mistral, etc., etc. The full contents of that community report are going to be going into more of the specifics. So Amazon Bedrock and AI model providers, Amazon Bedrock as a central service, Anthropic's role in AI safety and research, Cohere's NLP models in Amazon Bedrock. So what we can see here is that we're able to also capture and aggregate all of the individual data that we have in the nodes at these higher levels. So now we have all of the information needed to compile our full graph, which, as my scroll betrayed me a little bit ago and I flashed it on the screen, we can see here. This is the final visualization of all the communities, the nodes, and connections across the fine-tuning LLMs paper. Digging deeper into a higher quality version of this, what we can see are some of the larger communities include things like fine-tuning, that's to be expected, things like Hugging Face and OpenAI, and then we can see how OpenAI might be connected to something like LangChain or Google Vertex AI Studio. And then over here we have stuff like Amazon Bedrock. And then within Amazon Bedrock, we can see all of these different AWS things and stuff that is available through Amazon, as well as SageMaker and the different connections there. So we can see, PPO alignment as well down here, Meta, and some large community about financial stuff in GPT, as well as some smaller sub-communities that didn't necessarily fit into the larger overall graph. So these are just kind of subnodes on their own, which looks like it might include stuff like audio over here. This one is content marketing agency. We can see that effectively we've been able to structure our unstructured text into this complex graph that displays the main concepts, how important they are, and the different sub-concepts and their relationships together. Right off the bat, this is already a great way to visualize unstructured data because we as humans, of course, are going to understand a little bit more of how these ideas and relationships are interconnected with each other. So we can see where there are larger concepts or maybe different offshoots or tangential things and be able to just understand the structure of a lot of this stuff. But now that we have our unstructured data set up nicely as entities, relationships, and communities, what we can do is take advantage of all of these connections and the different groupings with different retrieval techniques. Contrary to traditional embedding-based RAG, what we can really do is take advantage of these multiple levels of specificity across our communities and the relationships between these entities as entry points to both see similar and related concepts to the different topics that we might be querying about. More specifically, now we're going to look at 3 types of search. Global search, which is going to use the generated community reports from different levels of the graph's community hierarchy as the context for our response. Local search, which is going to combine the structured data from our knowledge graph with the unstructured data from the input documents, as well as any relevant entity information for our more specific and granular responses, as well as drift search, which is a novel idea introduced by Microsoft that stands for dynamic reasoning and inference with flexible traversal, which is going to be an approach to local search queries by including community information within the search process. So we'll break down all of these now. As a quick note, while GraphRAG does have a Python package that we can use, I am just going to very simply define a function that'll wrap around the command line interface tool for all of our retrieval stuff. So this is more of a simplified and easier example, but it should still give us some results that we can analyze. So the first and most similar technique to traditional or regular semantic RAG is going to be local search. And what we can do now is take clear advantage of our graph-based approach. So in essence, what we're going to do is first search for the relevant entities to our query using semantic search. If you recall, what we did is actually embed all of these nodes using node2vec into a vector database. So we're still going to be using the vector database semantic search, but instead we are going to be returning back nodes. These nodes are going to become the entry points on our graph that we can now traverse. So starting at these points, we look at the connected chunks of text, which are going to be the chunks of text that the node was extracted from, as well as different relevant community reports that it is included in, other entities, and the relationships between all of them, as well as the different data that comes with those. The resulting information that we get that includes all of the relationships, community reports, and chunks of text that the entities are tied to are all going to be combined, filtered, and ranked to fit within our context window. And then that is going to be used as context for our output from the language model. So let's go ahead and run a local search with the query, what are tools for model initialization? After a few seconds here, we get a successful response back. So we can see that model initialization is a critical step for setting up LLMs for operation. And we can see some of the reports and entities that it actually referenced from this. And then more specifically, it tells me that Hugging Face transformers, PyTorch, and TensorFlow are going to be frameworks, and then also NVIDIA Nemo and Optimum by Hugging Face. I think that this is quite interesting because if you look back in the text at their explicit tools and libraries for model initialization, you can see that it only has Hugging Face and PyTorch and TensorFlow here. But it also managed to find relevant information from things like Nemo and Optimum, which talks about enhancing language model deployment efficiency. So there's definitely some concepts under here about initializing and monitoring language models. And then it was also able to pull things like the importance of model initialization, which is a big section that also was around the Hugging Face transformers part here. And so it's generally able to find these relevant entry points, pull the actual information that was relevant to my query, and then be able to combine it all into this final augmented generation response. So we know that our local search is going quite smoothly, and it's very much simulating what we would initially see with a traditional based approach, but augmenting it through all of the additional context that we're able to gather and the different approach to actually finding the relevant information with our knowledge graph. Our second search method here, global search, is going to be something that traditional RAG actually performs very poorly at. We can recall that through the clustering of communities during the indexing process, we created community reports as summaries of the different high-level themes across the various levels of these groupings, which allows us, in turn, to be able to answer queries about broad themes and ideas across our unstructured data. As mentioned, this is something that traditional RAG really cannot do because it only has the ability to return back the specificities from our unstructured text chunks. So what we're able to do with that kind of follows this process. Given our query, we can use the embedded community reports at a specified hierarchical level to return back the nearest or most similar community reports to that query. We then run a series of generation steps. Essentially what we're going to do is take the report and extract out the key points from the report in a numbered list. So a language model is going to create that numbered list for all of the retrieved community reports and also attach with it a relevance score to each point as to how relevant that point is to our query. This then goes through a MapReduce style approach where what it does is it ranks and filters these intermediary points, trying to remove the ones that are least relevant to our original question and maintain the most important ones. And then that final list of most important points is what's returned back to the language model as the context for its generation. So let's ask a nice broad question that covers multiple chapters in our knowledge base. How does a company choose between RAG, fine-tuning, and different parameter efficient fine-tuning approaches. And after another few seconds here, we have our response. So we can see our global search response of choosing between RAG fine-tuning and PEFT approaches. And so it says that we need to consider the specific requirements of the application, need for external data integration, computational research constraints, and the desired level of model adaptation and performance. Says the application requirements. And then what we can see here is that it's pulling from a wide variety of reports across the entire, life of this knowledge base. So really good broad question answer here, and we can see that it's pulling from a nice broad overview of the data. If we run the same query through our local approach, what we can see here is a little bit more specificity. For RAG, we can see that it's good for question and answer systems, customer support automation, and summarization tasks. And then for fine tuning, it says that it is a comprehensive process that includes all of these specific stages. And obviously we can see a lot of relationships there. And then for parameter efficient fine tuning, we can see that it offers optimizations for financial and environmental costs. So a lot more of these specific ideas are being retrieved in the local search, whereas the broader themes are being discussed in the global search. But what if we put it together with something like drift search? Drift search is a pretty cool combination of both global and local search. Essentially, it is going to include community information within the search process, going all the way down to local information. To follow this nice, lovely diagram that looks a little bit complicated at first, essentially all that's happening is that when a user actually implements a query, it is going to go through hypothetical document embedding, or HIDE here, where essentially what it's going to do is take the query, look at an example document from something like a community report, and generate a hypothetical document based on that query. That hypothetical document, instead of the query, is going to be the one that's actually embedded and used to run the first stage of retrieval. That first stage of retrieval is going to be retrieving the most similar to this hypothetical document, community reports. So we'll be starting at a global level. Then from all of these retrieved community reports that we have here, what we do is we generate an initial answer to the query along with follow-up questions. Then for each of the follow-up questions that we generated from this, we switch over to our local search. So we're going to be doing a same version of the local search that we just talked about a little bit ago. And each local search in this case is going to generate an intermediate response as well as new follow-up questions. This is going to create a pseudo refinement loop. What we mean by this is that hopefully we can get a little bit more specific within our actual refinement of the question by generating follow-up questions to explore. And each of these follow-up questions, both the global ones and the local ones, are going to be generated along with a relevance score. So all of these relevant questions are going to be the ones that we are more likely to actually explore when going through and navigating down this tree. And that should hopefully allow us to widen our area of data collection for the most relevant chunks of text within our graph. As we do this over a series of a couple steps, we can incorporate both our community level knowledge as well as our detailed entity and relationship data along the way, and really adapt our approach based on all of this emerging data that we're retrieving during the search. The final output that we get then is going to be an aggregate of all of the outputs here of the intermediate response, the questions and the answers that we're getting, and it is going to be ranked by their relevance to the original query. We're then going to use a similar MapReduce approach with equal weighting on all of these intermediate answers and pass the final aggregated response that is respective of the context window into the language model. So really what we're going to see here is a combination of global and local search with guided exploration to provide both broad context and specific details in responses. So let's go ahead and run the how does a company choose between RAG fine-tuning and different PEFT approaches through the drift search and see what we get back. And once again, after a few minutes, we get our response back. But This time we can see a major difference. We're starting to see a huge increase in the specificity of the output that we have here, as well as the length. So we're really going into the details here with this response. So it talks about the retrieving capabilities with RAG, the focus and depth of fine tuning, the resource efficiency of PEFT techniques, and then understanding the choice between them. So it's getting very specific and is able to combine a lot of really good details that are strewn all the way around the large document that we have with the specifics that are available in the local, more granular searches. So hopefully by now you can understand and see the power of representing your data as a graph and then being able to perform different kinds of searches on it, both the local search, the global search, and this modified combination of the two with a drift search. So how does this actually compare to just our regular vector database retrieval? Well, I have set up a very simple instance of ChromaDB and embedded all of the text documents from our original document, chunked in exactly the same way that GraphRAG chunks them, and put them into a retrieval function. My prompt then is going to be a modification from some of the existing prompts that are available within GraphRAG. So it's going to generate a response to the user, summarize all of the information, respond in an appropriate length, and then I also have it say if you don't know the answer, just say so and do not include information where the supporting evidence for it is not provided. So with that being said, let us put in the same question for how does a company choose between RAG, fine-tuning, and different PEFT approaches. We get back what is a little bit of a sorry response in comparison to some of the earlier ones that we see. We see just a simple list that's data access and updates, model behavior and domain-specific knowledge. Not a lot of very specific information. Does mention parameter efficient fine-tuning approaches like LoRa or DEFT are designed to reduce computational resources and overhead, but then it says, depends on the specific needs of the application, without going into a lot of detail or supporting arguments. And so while an answer like this is fine, it's not necessarily detrimental at all. I think I would much prefer the more detailed versions that include a lot of the good source information, like even the global stuff or the local versions here that are able to really dig into the specifics based on the specific information that it's able to retrieve. So with all that being said, let's summarize and talk about the benefits and drawbacks between traditional and graph-based retrieval augmented generation. So the benefits of traditional RAG are much simpler implementation and deployment. As you can see, much more simple than what we've got going on up above that. Works well for very straightforward information retrieval tasks, good at handling unstructured text data, and has a bit of a lower computational overhead. Some of the drawbacks that we have, though, are it loses structural information when chunking the documents. It can break up related content during that chunking stage. It has a limited ability to actually capture the relationships between different pieces of information, purely relying on the language model as it's generating its final response. And then it struggles when it has to reason or connect multiple facts that might be disparate or strewn across a document. So there are potentials for incomplete or fragmented answers due to these chunking boundaries. GraphRAG, on the other hand, has the benefits of preserving a lot of the structural relationships and hierarchies within this unstructured knowledge. It's better at capturing the connections between related information. We can provide much more complete and contextual answers, as well as some improved retrieval accuracy by leveraging and traversing a graph structure. This better supports complex reasoning across multiple facts and can maintain document coherence better than the chunk-based approach that we have. This also, as a benefit, has more interpretability due to its knowledge representation, which we can see over here. The drawbacks to GraphRAG are that it's much more complex to implement and maintain, requires a little bit more of processing to actually construct and update the knowledge graph, higher computational overhead for some of these graph operations, especially in the retrieval step. We saw that it took a lot more time than just the simple RAG to generate a response, may require some domain expertise to define some schemas and structures, and it's a little bit more challenging to store and scale these kinds of setups. A few of the key differentiators that we got is that really the knowledge representation is what comes down to it. RAG treats everything as flat text chunks, while GraphRAG maintains those structured relationships in a graph format. With context preservation, GraphRAG preserves much more better the context and relationships between different pieces of information compared to the chunking approach of traditional RAG. Reasoning capabilities, GraphRAG enables better multi-hop reasoning and connections of related facts through graph traversal, while we are more limited with direct retrieval in traditional RAG. And our answer quality, as we saw, GraphRAG tends to produce much more complete and coherent answers since it can access related information through those connections rather than being limited by the chunks. So really, in conclusion, the choice between traditional RAG and GraphRAG often depends on your specific use case, of course. GraphRAG is particularly valuable if you need to maintain relationships or nuances between complex information that you have that's unstructured, but traditional RAG is a lot easier to set up. GraphRAG, however, can give us a little bit more of the complex reasoning across multiple facets of information. At the end of it, however, GraphRAG really still relies on regular embeddings and retrieval methods themselves. So these methodologies don't necessarily replace each other, but they're more a complement to each other and can be used in tandem to really enhance your system. So when you're ready to take your simple proof of concept with maybe something like a simple retrieval thing that we had here up to the next level, you might want to consider a knowledge graph based approach. And so with all that being said, hope you learned something interesting today and are looking to implement a knowledge graph yourself. If you have any questions or comments, leave them in the comments below. If you liked the video, leave a like on the video. And if you want to support the channel and see more like this, consider subscribing. Thank you and have a great day.